Hello, everybody. Today we are back with another episode of the Code Force Speedrun, except we're not on Code Forces. So today I would like to go over the problems from the CS at Mines HSPC 2026, of course. Okay, so first comparing to the 2025 round, you can see you have pretty much like the same amount of questions, but the final question, Accomplice is Hard, was not actually part of the competition. And here we have, the same amount of 15 questions. And overall, I gotta say, the questions from 2025 were on average harder. So there were slightly, like more difficult questions involving like BSTA and some observations, greedy observations, and then this like kind of annoying math question, which was just hard to see because you didn't know like how the freaking mirrors worked. Like when you look at your reflection in the mirror, how does it work? Like I don't know when there's two mirrors, right? So yeah, basically there's just that kind of bullshit question. We got graph questions in both contests. Yeah, and overall you have just like a bunch of like weird questions too, and just like questions that test your memorization as well. Like this question was just like completely ass. Like what is this supposed to do? Like so on the bright side, we don't have like ass questions in 2026. So let's go over these nice problems. Okay, beginning with problem A. Also, a quick mention, I will go over this final problem will be problem E because this one is actually like a real ICPC question. So I would say like 2025 is still harder, but if you had to choose one question that was hardest out of all the years, it'd probably be this one. Okay, A, what does it want to do? It gives you the time in days, in seconds. It gives you the time in seconds and asks you to compute the number of days, hours, minutes, and seconds. Okay, so in problem A, it just gives you X seconds, and then you need to compute the answer and output the number of days, hours, minutes, and seconds. So first of all, we know that a minute has 60 seconds, an hour has 3,600 seconds, and finally, a day, you have precisely 86,400 seconds. 86400. So what you're going to do is you're going to first find how many days you have and then subtract off the according amount of seconds. So first you divide in by 86,400 to get the number of days, and then you subtract the number of days times 86,400 from the total seconds that you have, and then do the same with hours, do the same with minutes, and then finally just go ahead and output that. One note, you definitely want to make sure that you initialize everything to 0, otherwise you'll just insta wrong answer on the 0000 input. All right, that's problem A for you guys. Problem B asks, given the final row, the length of the bowling pins in the final row, how many there are, can you determine the total number of pins, only given the number of pins in the final row? Well, first thing you got to notice here is when you have one bowling pin, then there's one dude in the final row. So n equals 1, we have one dude in the final row. And guess what? When you have n equals 2, there are, you guessed it, 2 dudes in the final row. When n equals 3, yeah, you see the pattern. Basically, N is the number of number of bowling pins in the final row. So we just have to find the summation of k from 1 to n, and you know how this works. It's just the Gauss like series, sum series, which is k times k plus 1 over 2, and you output that. GG's, no questions asked. N times n plus 1 over 2, just, yeah, pretty simple. Okay, on to the next question, C. Finding fossils. All right, so you're given 4 integers, and it just simply asks, can you create a non-degenerate, non-self-intersecting quadrilateral with these 4 side lengths? So going back to, the triangle inequality, in order to form a triangle, you need to have, for example, these 2 sides be longer than the 3rd side. And you can just imagine, right? Like if the 2 sides were perfectly equal to the 3rd side, then you would just get a completely flat line. So just a flat line where you have this kind of situation. So this is not a triangle. So you need a plus b greater than c. And you actually technically need all of these conditions. You need a plus c greater than b and c plus b greater than a. But you actually only need these 2. You also need c to be greater than a minus b, which is just, that's basically the same thing. Never mind. All right, so the best way to deal with the quadrilateral is just to simply just do all 4 checks. Just make sure all 3 sides always are greater than the 4th side. So yeah, I do my 4 checks. So if the sum of any 3 sides is less than or equal to the 4th side, you insta-fail, and then you just say yes or no, depending on if it fails. On to D. Okay. Let's see. Building with boulders. Yeah, so you are stuck in a sort of maze with a threatening dinosaur who's going to come and eat you. You know the position of where you are and the position of the dinosaurs. So let's just take a look at sample 1. So you kind of have here, you guys are in one small hole, and the dino is here. So clearly the dino cannot get to you through the wall. And so how can you check this? So basically, you can either do a flood fill, so basically a DFS from the dino location and see if your location gets visited, or you can do the same thing where you do a flood fill on your location and see if the dino's location is visited. Basically, you're just checking if you and the dino are in the same connected component. So here, I just do a flood fill. I run my DFS from where the scientists are located, where we are located, and then I check if the dinos get visited. And if they do, it's not safe. And then if you can't get to the dinos, then you are safe. All right. Skipping E for now. Going on to F, time bumps. So here, it's basically just asking you, time compression is more dangerous than time stretching. So they're only interested in determining the total amount of time compression, which apparently it's just time compression occurs whenever the points increase in height. Okay. And then you just output the total amount of time compression. So basically, this is pretty easy. All it's asking you to do is every time the height increases, you just have to add how much it increased by to the total count. So pretty much you have an array, and then every time there's an increase. So if you have x and then y, and x is less than y, then you add y minus x to the answer. So every time this happens, when you're obviously going sequentially along the array. So this is just a pretty easy implementation question. All you got to do is loop n minus 1 times and check if array I plus 1 is greater than array I. If that's the case, you add the difference to the answer. Boom. Next. Problem G, teaming up Triceratops. All right. So it basically is asking you to remove one dino from either team such that you minimize the skill difference, which is just the sum of the skill levels of each team. So obviously in this situation, you might be asking the question, how do I know who to remove, right? How do I know who to remove? Well, you don't. But fortunately, there is more than enough time for you to loop through all candidates. You can loop through every single candidate and just subtract the skill level from his respective team. And then you can brute force the answer, basically. So you have team A and team B. Say you have like 1, 2, 3, and 4. So the way you can do this efficiently is you can first find the skill level of A, which is team A, which is 3, skill level of B, which is going to be 7. And then what you can do is currently just say like the best difference. So like the minimal skill gap is currently at 4. Well, actually, you have to set this after you take one out, but basically you can first start it off at even just 1e9 infinity, big enough number, and then say we remove 1, right? So you first loop through everybody in team A, and then you can loop through everybody in team B or vice versa. First take the first guy out, so then if you like remove 1 from team A, you're gonna subtract from the skill level of A accordingly. So now this is 2, and then the other one is still 7. So now you can update the min, and then make sure you keep track of the index as well. So here, if the difference, which is going to be 5, is smaller, we can update the min to be 5 now, and then keep our IDX. And the final solution IDX is going to be 1, and you track the team as well, A. So obviously after you loop through here, the best answer is going to be removing the 4, because that obviously gets a sum of 3 and 3. So you remove 4, and then you get 3 and 3. And then finally, you just make sure you track your index and whose team the best referee removal came from. And then you should have the answer from there. Yeah, not too interesting. As long as you see the brute force, it should be completely fine. Yeah, the main thing was just simply tracking the final answer's team and index, and then you have to base it off of the best score after removing that player. All right. Species survey. In this question, we are tasked with checking. Well, we are tasked with all these queries, and simply, it first tells you which species and family each dinosaur corresponds to, and then it can ask you how many dinosaurs are there, or how many, or the total number of dinosaurs of a family, or the total number of species. Total number of dinosaurs in a given species. So once again, this is just pretty much a simulation question at this point. You're just simulating. If they say like, well, how do you simulate? You have to track the total of each species, and then you just have to track as well the total of each family. Total number of dinos in both of these. And if you do that correctly, you should be able to output the answer pretty easily within the time limit. So here I update the count for the species, I update the count for the family. And then whenever it asks me to output, how many are in each species or family, I just output the answer accordingly. So you just have, as long as you track these two in a map, you're chilling. Okay, here comes one of the more interesting problems. Micromouse. Micromouse. In this problem, we are given a mouse, and it's an interactive question. The only the three things you can interact with are either move the mouse forward, or you can turn left and turn right. It's not spelled R-I-T-E. Okay, move forward, turn left, turn right. And the interactor will respond with success, failure, exit based on the result of the move. So what's interesting here is it's a maze problem, but it doesn't give you the adjacency list. It's not asking you to solve the maze like given your current starting location and where the exit is located. You don't know anything about the maze other than the fact that you're somewhere in it and it's 100 by 100. And to make things worse, you only get 10 to the 5th commands, but that's more than enough, you'll see. So let's go over the first sample. Okay, it looks like a hangman. But basically there are only 4 nodes, and then technically here's the exit. So first, you're facing towards here. So the problem with this problem is you don't know the maze at all. Like you have to interact to figure out your surroundings. Like what do you even do here? Like I don't know my position in the maze. I don't know the exit. I don't even know the maze itself. There's no representation of where the blocks are compared to the previous problem where you have hashtags for walls and then dots for safe places. There's none of this. There's none of this to help you. So that sucks. What are we gonna do? Well, first you might think about, all right, if I keep walking in random directions, will I eventually make it out in 10 to the 5th moves? Well, the answer is actually no. A 2D random walk, well, you're guaranteed to return to the same place you started. You can always return. But the probability that you'll make it out just randomly doing the MT19337 or whatever number that is. You're not going to make it out based on random chance. That's super low probability of happening. So we need something that is guaranteed to work. And that's where it gives us a very big hint. In this question, it says there's a sign that says between every pair of spaces in the maze, there's exactly one simple path. So what that's telling us is there's no cycles in the maze, or quote unquote cycles. If you walk, there's no cycles. Yes, there's no cycles in the maze between any 2 nodes. If you walk in one direction, obviously there's a cycle if you just keep doing this, keep going around in circles. Then sure, you go left, right, left, right, left, right. So one strategy you might think about doing here is you might try and remember some from a strategy book, a maze solving algorithm that was really simple, and all you do is you keep your left hand to the wall, and then you just keep having your left hand on the wall until you make it out. And in this case, it actually does work. Suppose we're facing forward, suppose we are facing this wall and then we turn to the right. So we're facing this wall right here. and then we turn right, then the wall is to our left. And then if you keep following this wall, you're going to get out. And then I guess like in using the same logic, you can also have your right hand towards the wall, in which case you'll loop through like this and also get out. Let's see if the same logic works over here in the second test case. Oh, I drew this so off scale. Okay. It's a little bigger this time, but you see, we have our left hand on the wall. Well, not yet, but we're facing this way. But suppose we turn right first, then we have our left hand on the wall, and then you can just keep your left hand on the wall. Which does actually work. So now we have found our strategy, but how do we implement this? So the difficulty here is you have to like do two steps. The first thing you have to do is actually get your left hand on the wall. And the way you do that is you first move forward until you hit a wall and then turn right. So first we hit a wall. That means the wall is in front of me, not on my left hand side. I turn right to make sure this wall is now on my left hand side. And then while I'm not out, what I first got to do, so the first thing is, okay, suppose we have a wall here to my left-hand side, and then I'm facing this way. Okay, so first thing you have to check is, can I go left? You'll see why, because if you first move forward, that's not going to work because you might like skip something. But here, yes. So first I have to check if there's a wall on my left, because if I don't, then I will I'll just completely move past this wall here. So if you're here and there's a wall, so if I'm here and then there's a wall to my left, then I have to first turn left and then see if I can move forward, because if I try to move forward first and then turn left, like suppose this wall wasn't here, then I would completely be in a different section of the maze. If this wall wasn't here, I'd be here now, and then I tried to turn left and I already completely missed following this wall, and that could actually get you in a cycle in some test case. Okay, so we check if we can go left, and if we can, we immediately go to the left. We turn left and move forward. So suppose I'm like, I take my first step out and the wall has kind of just ended here, and I immediately go follow the wall. And then after, okay, so if I have to first move left, and then suppose I moved left, and suppose I could not move left. Suppose there was a wall. I was still following the wall. Then you have to make sure you turn right, and as soon as you can move forward after turning right, you have to move forward. So it's kind of like at every step, you have to first make this like left hand look to see that you're still following the wall, and if you are, and then of course you are following the wall still, and then you have to redirect yourself to the right and then keep following that wall. And then here's, yeah, so if it is successful, then we don't check to the right, obviously, because like after you moved once, you have to check again to the left first. So that's kind of like how you can hug the wall to the exit. Okay, Frobnicators. Let's see. Problem J asks us to simply output the lowest possible cost to buy n of the integers given. So here we are given three integers, 2, 2, and 1, and we got to find the minimum cost to buy two of them. We only want two of them. So we can just take these two. And then once again, suppose these were all ones, the sum would be 3 if you were taking all of them. So here, it doesn't matter which one we take. It only matters, I mean, it doesn't matter which index we take. It only matters the cost of the arrays, I mean, the integers we take. So clearly, the strategy is to sort the array 1, 2, 2, and then just take the first however many you need. Okay, next problem, population tracking. Population tracking. So in this question, it's a simulation question, and the dinosaurs, when they're born, they're 0 years old, and then they die at age 40. So they live for 41 years. Yeah. And what's interesting is they can only reproduce if they're greater than 10 years old. And then you're given the ages of the original dinosaurs and how many years you have to simulate for. So suppose you're given, you simulate for 1 year, and you have these 2 dinosaurs that are at age 9 and age 10. So this is at time equals 0, year equals 0. So on year 1, it tells you the first thing you got to do is update the ages. And then the second thing you have to do is, obviously, it doesn't tell you here, but then you have to check actually who's dead first. And then you have to add all the children. So after the first year, there will be 2 adults at 10 and 11, and then 1 newborn, age 0, at year 1. So now you might be thinking, okay, so why don't I just simply simulate this? Like, I can just chuck everybody into an array and then, increment the array. Or what I do is I would make a copy of it and then only push the alive dinosaurs into it and then take its size and then add however many children that would be born. But the issue with this approach is you have this insanely large number, and this is like up to the long max almost. So there's no way you're gonna have like 10 to the 18th amount of elements in your array. Like, that's definitely time limit exceeded and memory limit exceeded as well. So can't do that. But guess what we can do? What's the most important information we need to know? It's just the ages, right? So all you need to actually track is you just need a array length 41 and just track how many dinosaurs are at each age from 0 to 40. And then when you transition from 1 year to the next, all you have to do is just simply take the amount of dinosaurs at, for example, age n minus 1 and just move it to n. But you do this in reverse, so then you don't accidentally overwrite something. And then all the dinosaurs at age n, just at the final age of 40, they just you just straight up overwrite them because they don't matter anymore because they're gone now. They're dead, and then you just overwrite them, and then you just overwrite everything. So you make this update, and this only takes 40 operations pretty much. And after that, you can easily calculate the adults from 10 to 40, and then you can just add however many newborns to the 0th. Or not even plus equals, it's just equals. And you just set array 0 equal to the number of newborns, and then bam. At the very end, you take the sum, and then you output it. That's pretty much it. Next question, L, Dino DNA. Yeah, so this is a tough one. You're given N and M. So N is basically your word bank, and M is a word. And not only do you have to output if it's possible or not, you have to actually give a valid construction. So let's take a look at this. We have the word bank, which is CT and AGG. So everything has to be made out of these two guys. And then you can take a look. Can we make CT-CT? And the answer is yes. The CT-CT, you just take two of those. Take two CTs and you have it. You can easily also make AGG-AGG-CT because you take two AGGs and then the final CT. That's cool. And then CAGGT, obviously you can't make that. So you might be thinking like, okay, well, what do you do? Suppose you have like kind of like redundant word banks, like you have like an AB or something kind of like AB or something like that. Like if you have a redundant word bank and then you encounter something like AB, suppose like you counter this, right? The problem is it's like if you look at only the first two indices, you're like, okay, well, this works. But then if you wait and you look at all four indices, but then you're like, oh, that works too. And then you run into some like problems. So suppose you're in a situation where it's like you always take the shortest one. So suppose like you have like an A and an ABC, and then you're trying to make ABC. If you only take the shortest, like substring and you match it, you're gonna match this A here, and now you're left with BC, and now you're screwed because you don't have a BC. There's no BC here. There's no BC in your word bank, so you immediately fail. But then by similar greedy logic, if you're like, okay, well then how about I just take the longest one first, right? So suppose you have like A and then B, or if there's four A's here. So then suppose you try to take the longest one. Suppose your word bank is like you have A, B, and then you have A, and then B. So you're like, okay, I go as long as possible. So bam, I put this here. But then you're like, oh shit, there's a B left over, but I don't have any B's. A lone B. You don't have this lone B over here. So the conclusion we got to make is greedy doesn't work in this problem. So greedy is going to fail. So because you cannot do a greedy solution, it might lead you to think maybe DP. And this is surprisingly like similar to knapsack DP knapsack because you're kind of like you have like these like coins with CT and AGG, like these values printed on them, and you have to like make a big chain string, like a big long string out of like these smaller like substrings. So what you have to do is you have to first do a DP array where DPI is can you make the substring, can you get to the substring ending at I, and this is going to be true or false. So can you achieve this substring of the goal string ending at I? So for example, DP of 1 would mean can you make AA in this case, and then DP of in is like can you make the whole thing, and then how do you do the transitions? Well, so like you have like DPI, you have to like, so DPI is going to be true. So if you have, So you can do this check for each substring in the word bank. You have to first make sure the DPI minus the length of that substring is true. And you have to make sure that the substring is going to be equal to the original string, well, the original s dot substring. So like the positions, so the two strings have to be equal. It's basically like you're adding this substring to the previous string. So like whatever, so the current index, or this, okay, sorry, it's not the syntax. So starting at I minus length, and then you go for length. And here's my implementation for that. So as I'm doing my DP here, so first loop is the ending point. Second loop is for each substring in the word bank. And then I check if you can go like to the previous part, like basically like you have your previous the previous substring and you're adding this new substring on. So like if I can already make the previous substring and the current, and then the next part of the substring is equal to the substring in the word bank, then I can set this whole substring to true. And then finally, you can also track how you can actually, get to this substring by just simply adding the index of the substring that you chose, that was chosen to make this step. The sequence, just push back the index here. And then finally, you output that whole sequence if it's not impossible. Bam. Problem M. Pangram Cipher. So first, it's basically just telling you the quick brown fox jumps over the lazy dog. So all of these letters in this original string correspond to these letters here, down here. So it gives you 26 letters first, and then these correspond immediately to here, these characters in the lazy dog string. So for example, you see like here so here the X corresponds to the T here. The L corresponds to the H, and then this N would correspond to the O here. And you can even see like the X immediately corresponding to the T, and then here's an XN and XLO, and then there's both T's here. So what we're doing is you just have a map of one character, and then it corresponds to the other character in the other string. And then you can easily just convert all the test cases into the correct word. This cipher replaces every letter with itself. Yeah, cool. Pretty simple. Laser maze, problem N. Okay, so here's another nice little graph problem where you have to simulate the path of the laser given which row it is shot horizontally to. So if you have a single mirror placed here and the laser goes in at row 2, it's going to get shot up and then exits here on column 2 as well. And then once again, if you have like this setup, and you still shoot it at row 2, what happens is it goes up to the right and then down, and then also to the right. Okay, so once again, since there are only 2 cases, you can either have a mirror that's, you know, this backslash or the other backslash. And then you only have 4 directions where you could potentially hit this mirror. What you gotta do is just break everything down into cases and handle each one separately. So here I first start off the laser. If it first hits a non-mirror block, then I just keep it moving. And then I do the 4 cases if it hits one of the backslashes and the other backslash. And then finally, since I know the final position, I can just, and the final direction, I can easily break the final answer down also into the 4 cases and just output the correct one. Yep, that's that. Rex knockout, problem O. So this is just another simulation problem. Basically, it's not the same as, well, yes, it's basically just regular knockout. You check, but it's asking you how many balls are shot or how many turns the game goes on for. So suppose we have 1, 3, 4, and 2. So these 2 guys, they first shoot. 1 will get knocked out by 3, and now 3 is up here. 3 and 4 shoot. Now 4 knocks out 3, and then 4 and 2 shoot. 4 makes it, so he goes to the end of the line, and now they shoot again, and then only 4 is left, and he has 1. So this is okay. So how many shots were there? It's 5 shots. So this is the first shot. Here's the second shot. Here's the third shot. Here's the fourth shot. Here's the 5th shot. Okay. All right. Well, the first hoop is made by the Rex with power level 3. Okay, so he goes to the end. Oh, okay. So if you knock someone out, you actually go to the end. So I just simulated that one incorrectly. So effectively, all we have to do is just simulate the game correctly. And you can do this by using a deck. So the deck is really nice because it has a pretty efficient like pop front and push back, and then you can push front and probably pop back as well. So what's nice is you can just first check who is winning. And the way you do that is you just have to compare first and second. So the immediate 2 people, like at the very beginning of the deck. So if the first person is bigger, I mean, he has a bigger number, he has better skill level, he's gonna win, and he gets pushed to the back. And then the second person who didn't win is at risk of getting knocked out. But then in the other case where the second person's stronger, he knocks out the first person. The first person's gone, he's not coming back. But then the second person gets added to the end of the deck. And then, yeah, that's a pretty efficient simulation here. So if I were to go back and just do this correctly, so first you have 1 against 3, 1 gets KO'd, 3 gets the move back. So one person's always moving back. 4 against 2, 4 wins, so 4 goes back. 2 against 3, 3 wins, so he actually does go back. And then 4 against 3, 4 wins, he goes back. And then 3 is KO'd. So this is 1, 2, 3, 4, 5. Okay, easy. Did I do all the questions? No, I did not do Raptor Pack. So now we're on to the hardest question of all. How to deal with the toxic Raptor Pack question. So, in this question, we are given just only two integers, in and out. And you're trying to place these endpoints on the 2D grid such that all the columns and the rows they occupy. You can find a row or a column. You can find a row or a column that has exactly from I raptors in it, but the I has to go from 1 all the way to M inclusive. So increases by 1 at a time. So you need this 1 less than I less than M, all the I values in between, and the raptors have like sharing this X value can only sum up to one of those I values. So here you have all the vertical, if you check all the vertical values of these raptors. So for example, X equals 1, there's 1 raptor. So 1 has been satisfied. X equals 3, there's 2 raptors. So now 2 has been satisfied. But X equals 4, the first raptor has already, 1 raptor in like either horizontal or vertical group has already been satisfied. So this guy kind of didn't help at all. But it was not the vertical one that he was helping with. It was actually the horizontal line, Y equals 1. So now there's 3 of them here. And then in the case where it is impossible, for example, you don't have enough raptors, you have to actually output impossible. So now let's actually just take a deeper dive into problem E and see what's so annoying about it. So the lowest value of M they give you is 3, and then N equals 4. Is that the best we can do? Well, could you have possibly done this with 3? And the answer is actually no. And the reason why is, so you have 3 all lined up here. So no matter what, you have to line these 3 points up in a line, because if you don't, then you're not going to be able to satisfy this constraint of having even 3 people either in the same vertical line or the horizontal line. It would be impossible if you didn't do that. Because if you do like an L shape, that's not going to work. If you try to do if you put everyone just here, you only have 2, or you only have 2. It doesn't matter how you put them. If they aren't in the same line, you can't have 3. So that is not satisfiable. So M equals 3, when N equals 3, you cannot satisfy M equals 3 because you can only make 3 in 1. You can't make 2. So you need an extra person to make 2. So then the question is, okay, so what if M equals 6? You might be like, okay, well, so what do we do? What's a natural way to do it? So how do we minimize the amount of points I draw? So first I can make 6. You might be like, okay, then I can try and make 5, right? Then I can try and make 4. Then I can make 3, and then I make 2, and I make 1. That's pretty nice. So now we know that a construction of m times m plus 1 over 2 is going to work. So that is enough. So I made 1, 2, 3, 4, 5, and 6. That's pretty cool, right? But can we do better? And the answer seems to be yes. Because then you consider okay, what if I do something okay, this is so bad. 1, 2, 3, 4, 1, 2, 3, 4, 5, and 6 here. So now I have 6 here, and then I have 1, 2, 3, 4, 5. So this is better because I literally shaved off from here. I have 1 plus 2 plus 3 plus 4 plus 5, and then plus 1 instead of plus 6. So I literally shaved 5 off. And you might be like, oh, this is pretty nice. Why don't we just do this? This has got to be the answer, right? The answer of 1 plus 2 plus 3 plus 4 is 10, so this is 16. And then they did 13, which is clearly impossible, right? Because that's way lower than 16. But then if you tried to do this construction, you would instantly also get a WA. That's what I tried. I got a wrong answer off rip because I tried to do this construction. All right, so suppose you did think this was the correct construction. So suppose you tried to submit this incorrect construction. So what do you do with all the extra points that aren't these 16 points? What you got to do is you can just set these extra points just diagonally at a very far away location, because if you do it diagonally, they don't interfere with each other. So this is always contributing 1, which is fine because you're already contributing 1 down here anyway. But if you put them all on the same line or same vertical or horizontal line, like there might be a lot of them, and then you suddenly contribute, for example, like m equals a very big number when you can only contribute m from 1 to 6, and you contribute like m is 100, and then you get cooked. All right, so what is the actual correct way to do this? Well, we can try and put 6 dudes here. All right, and then I can put some other guys over here. Like I can put 5 here. Where do I want to put 4? Let's just put 4 here. Where's 3? I'm gonna try putting 3 here. So what do we have? 1, 2, so we got 6, we got 5, there's 4, there's 3, there's 2, and there's 1. So how many points was this? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 6, 6, 12, 13, 14, 15. All right, that's pretty nice. But is that the best that we can do? Well, no, because I see that 1 point here is extra. You can either take this one or take that one off. So here, this is the best solution. You got 1, you got 2, you got 3, you got 4, you got 5, you got 6. So this is actually n equals 14. So that explains why this 13 is impossible. Well, the real question is like, okay, so first of all, it's really hard to know even how many, like what is the minimum number of points I need to satisfy a given m. Like for example, they give you m equals like 12. Like I don't even know the number of points. Like I don't even know the number of points for m equals 9. And then how do you even come up with this construction? Like this is just so abstract. It's like you have to keep guessing. Like maybe with only like 14 points, I can eventually like, come up with the right answer. If you had like 300 points, like how am I supposed to even construct anything? So now we're gonna have to start making, more concrete like, like designations and try to make some observations here. So first, if you let k be the number of groups, so like this is just like m, so like you can let m be the number of groups, then you know that you have to have r rows and c columns sum up to m, because you can have, so like either you have like 2 rows of, so either each number has to appear in a row or a column. So that's pretty much what it's saying. All right. So we know like the total sum. So okay, first the number of rows plus the number of columns has to equal the total number of groups. And then the sum of the values inside these k groups, originally, once again, remember, from the bowling pin problem, the sum has to be k plus 1 over 2, k times k plus 1 over 2, because that's just simply 1 plus 2 plus 3 plus 4 all the way down. So like that's how many points we had originally. But notice every time you have an intersection point, so where this row and this column intersects, you get to subtract. So like this is total. You get to subtract the number of intersections from there. And your goal is actually to minimize this. All right. So the second thing, so this is like the first thing that we want to do. The second thing we want to do is to note that each row contributes, each row contributes the minimum of the row size and the number of columns, and take them in. Same thing with the columns, is the column size and the number of rows. So basically, since there only are rows, each column, like suppose you have a max column capacity, you can only intersect these R rows. So like the minimum contribution so like this is the minimum number of intersections you can contribute. Sorry, I meant to say this is the maximum number of intersections you can contribute, which is the minimum of the size of the row or column, and then the total number of columns or rows. So finally, if we want to maximize the number of intersections, we have to come up with a construction, of rows and columns that kind of works this way. So how do we do that? Well, it's like, first things, it's like if you try to place like all the large numbers in the rows, for example, like this is not exactly ideal, because like, yes, you'll have very, very large I here, but then your column size is going to be really small. So your column size is going to be the limiting factor. And the same thing, if you try to maximize this column, like with all the big numbers, like 9, 8, 7, 6, 5, but then your rows will only have like 4, 3, 2, 1. And then the row size is going to be limiting how many intersections you have. So just by guessing, you can, for example, you can let the rows be all the odd numbers, 9, 7, 5, 3, 1, and the columns be the even numbers. And this is nice, because this is how you maximize the number of intersections. All right. So then we can also try to calculate the row capacities and the column capacities. So how much could this actually contribute? So you can match this row with these columns, right? But you have to but you can't do that yet because you don't have the capacities. So what are the capacities here? First thing I like to do is I like to first hold one side constant. So suppose we're trying to match the columns to the rows, and you have like the column capacities, which are going to be 5, 5, 4, and 2, because these top two are maxed out by the number of rows there are. And then for the rows, you're going to have 4, 4, 4, 3, and 1. And then I'm going to match over here. So like if I match this column with this row, then it's going to decrease the capacity of both the row cap. So this is going to, the column capacity is 0, but then the row cap, these are all going to decrease by -1. And then once one of these reaches 0, I cannot keep adding him to an intersection, because I need a single row to only have one number in it, right? I mean, only one raptor in this row, for example. Then I can't add another raptor here in the same row, because that would make it 2, and now I can't achieve I = 1. And so the same thing, you're gonna match as many as you can, right? Because this is already gone. Yeah. So basically, this is what you're trying to simulate, and the way you do this is you throw these guys into a priority queue, and then you pop off as many as you can. Yeah, as many positive ones as you can, and you try to match these. And then what happens is, for example, here you have a column = 1, and if you let these have like indices of 0, 1, 2, and 3, and then indices of like 0, 1, 2, 3, and 4. Every time you get a match, you can actually just store the coordinates. So these are literally the coordinates you can use for the final like graph. And if you did it the way that I'm doing it, I'm pretty sure what ends up happening is you have the columns pointing upwards. So like if you want to increase a column, all you have to do is just add along the same x value, and then if you want to increase the number of rows, if you want to increase the number of raptors in the rows, you just have to add to the x value. And it actually doesn't even matter if the final point. Okay, I'm not there yet. Okay, so first we got to simulate this. So we have the points 0, 0, 0, 1, 0, 2, 0, 3, and 0, 4. And then on the second column, okay, so the first column matched with everyone. On the second column, unfortunately, this guy's gone now. So you can only match with 0. Okay, let me see. You can only match the first one with 0, 1, 2, and 3. Okay, the second column you can only match with, okay, it's the same, 0, 1, 2, and 3. Okay, so now the 3 is gone because it's been used 3 times. And for the third and final column, you can only add, well, since it has a capacity of 2, you can really effectively only add to 0 and 1. So here, what do we have? We have, there are 4, so we got 0, 1, 2, 3, 4, 1, 2, 3. So we got points. So the first column has 5. The second column has these 4. The third column has these 4. And then this one has only 0 and 1. But here are all my intersection points. So notice that all of these points, like, they're supposed to, be like the intersection points for this specific column and row. So these are the only points where we're supposed to have intersections. And then how do you find out the rest of, like, where the rest of the points go? Well, since you already know all your intersection points, you have like x, y, and yi, you can also set up like the total number of points you have. So for example, in the columns, in the rows, we gave them all the odd numbers. So like every time you can just loop through all your intersection points and just subtract off. So you have like the point x and y. So like here's the column index, so the column index and the row index. So like every time you have like the corresponding row, you can just subtract 1. Like you subtract 1, and then whatever you're left with, you add to the correct row. So if like anything left on the rows, I'm gonna have to add down here. So let me add these in stars, for example. Like I add down here. Okay, this is not actually correct, but, and then all the columns I add up here. And then finally, the rest of the points you can just add over here, completely out of range. So let's go through the code of how to do this. Like, this is actually quite annoying. So first I have to like find my capacity sizes, and then I sort them descending. I first chuck, for example, the rows onto the priority queue, and then I extract my intersection points by doing the matching each column to the rows. And then you can check how many are remaining. Let me try and output this. So how many rows and columns are remaining? And then you can add the rows and columns accordingly without, you don't have to like specifically add it to any specific coordinate. You don't have to do that. Like as long as it's on the same row, it's good. Okay, so take a look at these first 2 lines. So the first one is how many rows I have. So how many raptors I have to place on the first row, which is 6. So here, the first row, you need to put 6 of them here. So 2, 3, 4, 5, and 6. Second row, I have to put 3. And the third row, I have to put 1. And then here on the first column, I have to add 3 dudes. On the second column, I have to add 2 dudes. And the third column, I don't have to add anything else. So here's the final like construction. So for m equals 9, here's the final construction. So I have 9 down here. I have 1, 2, 3, 4, 5, 6, 7, 8 over here. Here's 7. Sorry, that's not 7. This is 6. This is 7. Where's my 5? 1, 2, 3, 4, 5, 6. The 5 is supposed to be, okay, sorry, there's supposed to be a point here. The 5 is here. Okay, so I actually like, so in the priority queue simulation, there was actually no point down here. There's a star here. Yeah, anyways, I kind of messed this one up. But basically, in the simulation, you'll get these points, and then it does add up correctly in the end. So yeah, here's 5, and then 4, 3, 2, and 1. So this ends up working. So like the hardest part of the problem is really just, first of all, like finding the minimum in required, like given the m. And this is really hard to do because you have to do like the matching of capacities of like the rows and the columns, which is really difficult because you have to first realize like you have to like put all the odds in one side and then put all the evens in the other group, and then you're like trying to match this accordingly. And then if you can match it, then that means that one of these points is an intersection. And then you have to subtract off how many points you've already placed. Subtract off all the points you've placed from the original capacities. And then you have to like, and then you have to add the remaining unplaced points into the correct rows and columns. And if you finally do that, then your answer, then you can just output this construction, and then all the remaining points very far away. And that's all you got to do.